파스칼 코리아의 정희정 이사님께서 Pascal's Full Stack Neutral Atom QPUs and Industry Use Cases 라는 주제로 발표해 주시겠습니다. May I have your attention, please? We will now begin the second session of the 연세퀀텀위크 2025 industry session. In this session, Dr. Hee-jung Jung from PASQAL Korea will give a presentation on the topic Pascal's Full Stack Neutral Atom QPUs and Industry Use Cases.
Okay, thank you very much for your introduction. Hi, I'm Hee-jung from PASQAL Korea. I joined PASQAL about a year ago as a head of quantum computing, and I feel happy to share our business and technology with you today. Okay, so I'm always starting by introducing myself as an experimental physicist as a training. So my background is experimental AMO physics. So hopefully we can discuss about some physics during this speech. Okay, I'll talk about our company and technologies, and then selected use cases and algorithms. Okay, so you can hear me, right? Okay, so PASQAL is a unique mix of science and technology. So our mission is to engineer our QPU to make them reliable and stable and industry grade. So we come from a legacy of scientific excellence, as you can see in our co-founders. So Professor Alan Aspect got Nobel Prize in 2022 because of his early experimental demonstration of quantum entanglement in 1980s. And Professor Alan Aspect is one of a pioneer in neutral atom quantum computing. And George Olivier Raymond, our CEO, co-CEO, he contributed early demonstration of single atom trap 25 years ago. So, and then he built his industry career right after his PhD. So, Professor Alan Aspect likes to say, when there are no fundamental limitation, engineers find a path. So, indeed, all the fundamental discoveries have been made in neutral atoms to control, entangle, and manipulate them. So, now we come into the engineering phase. So, starting by 5 employees in 2019, PASQAL raised 25 million euro Series A and merged in 2021, and then merged quantum computing algorithm company Q&Co in 2022. And at the end of the year, Professor Alan Aspect got Nobel Prize. And early next year, PASQAL raised 100 million euro Series B, which gave us significant momentum in developing our technology. So last year, in terms of technology, we can think about the number of qubits. We successfully arranged more than 1,000 atom array. And also, last year, we have a lot of business highlights, including IBM. We start with IBM collaboration, and then we delivered our QPU to 2 HPC centers in Germany and France. And then Saudi Aramco purchased our 200 qubit device, and then will be delivered end of this year. The end of last year, we partnered with CMA CGM, which is largest transport company in the world. So, okay, so then now, after 5 years, we are almost 300 employees. Okay, as a global company, PASQAL located in Paris. The headquarters is located in Paris and has subsidiaries in US, Canada, and South Korea and Saudi Arabia. Okay, and we have more than 40 clients and partners, and applied more than 55 patent applications. And I'm based in South Korea, which covers Asia-Pacific regional activities, including R&D. Okay, thank you. So PASQAL is a full-stack quantum computing company. You heard about full-stack quantum computing company. So from the hardware to the software algorithms. So for example, our Orion Alpha generation is 100 qubit analog mode for rapid prototyping and testing. And Orion Beta and Gamma lineups are more stable, 100 and 200 qubit analog mode. And then the Bella and Pegasus lineup will be used to demonstrate quantum advantage in the 400 qubit and 2,000 qubit range. And then we are, based on the quantum error correction, we are developing 128 logical qubit Centaurus model by year 2028. In addition to selling and installing our physical QPU, we offer cloud access and then libraries and platforms. Platforms manage our graphical user interface and software integration. And we also support technical support and the maintenance for the machine that is installed. We also provide R&D support to our industry customers when they try to solve their industrial problem using our quantum algorithm. So for example, we work with LG to solve fluid dynamics using so-called differentiable quantum circuit algorithm. And with BMW, we work on material deformation. With Thales, we looked at satellite mission planning. With BAS, we start to solve weather modeling. And then with French bank, Crédit Agricole, we provide some QBoost algorithm for their risk management. And then with POSCO, South Korean global company, we looked at process optimization. And with Panasonic, we studied quantum chemistry, and etc. So this map shows our customers, customer world map, including the real QPU sales. Last year, we also had a remarkable achievement with the major player in the global industries recognizing the PASQAL's capabilities. So, for example, we signed on a contract and agreement with Saudi Aramco last year to install 200 qubit QPU in Saudi Arabia. And we also delivered Orion Beta generation, which is 100 qubit to Yonsei in France and L.O.V.E in Germany, which are HPC centers. These 100 qubit device will be connected to their classical supercomputing resources. So we have to orchestrate workflow between classical and quantum resources. For that endeavor, we are partnering with IBM to define the interface and standard way to combine those two together for quantum-centric supercomputing. So this will ensure hardware agnostic user approach, so regardless of different types of platform. So which we might need. We don't need to care about which type of quantum computer. We just would like to solve the problem, right? So, so that signals game changer for business. So other big tech companies, the big tech companies start to collaborate with neutral atom quantum computing startups after this. So why is it became a game changer? The first thing is the high performance computing. So this workflow will combine different type of resources. We already have today GPU and CPU integration. So we have to make sure that we can successfully integrate our quantum computing resources to their pipeline. At the same time, to boost the performance of our QPU, we work on qubit scaling, addressability, and repetition rate. Also, we are also developing gate-based universal quantum computing using error correction, gate operation, and interconnect. We also develop softwares, and ultimately, we would like to increase usage and QPU hours for our customer through the cloud with several QPU generations. And we also build collaborative platform for our customer and users to learn and use our algorithm to solve their problems. We recently opened PASQAL community so that you can join with your email account to use it, and then hope you enjoy. Okay, so this is the roadmap that I've been talking about so far. So we follow the roadmap. So technology roadmap and product roadmap. We separate these two so that I talked about 1,000 qubit achievement last year. And then it'll come to the 10,000 qubit in the near future. And then in terms of the product, I already talked about first generation, second, and third, which third generation will be deployed to Aramco at the end of this year. Okay, so how we went from experimental research to the industrial integration system. Okay, so our flagship product are hardware products, Orion generation of processors. What you see here is our first generation Orion Alpha device. This industry device is connected online, the cloud by cloud, and running at 90% of uptime in production mode for our user to implement it in their use cases. Okay. Oh. So I'll show you the short video clip to show you, show you the inside of this device. The main part of controlling, processing our qubits, which is atom inside a vacuum chamber. So laser lights comes in and then control each individual atoms that I'm going to talk about, and then processing and read it. So this device consists of optical module inside, and then the electronics controller, and in this on slack on the left-hand side. And then, as you might notice, this is room temperature device. We don't need extra cooling or cryogenic cooling device, so that it ensures that we only need low powers, like in the level of kilowatts. So it's very running at ambient environment, which is a huge merit. besides all the components and then electronics, we can buy it from the industrial supply chain very easily. So this shows the schematic. This schematic shows the technology of our device, which is neutral atom quantum processing unit. So our qubits are individual atoms that we control using laser light. So everything happens from this vacuum system where in a very low pressure, you may feel at the surface of the moon. Actually, it's 10 to the minus 10 torr. And then we control individual atoms and individual rubidium atoms and with a tightly focused laser beam. We call it optical tweezer array. And these technologies have been made for last decades. Okay, for encoding quantum information on those atoms, we need additional laser light. And okay, so the 1 or 0 of our atom is the electronic energy level of a single atom. So, okay, excuse me. Okay. So those two, we use laser light to induce the transition between two. And then for the readout, we can use standard camera like EMCCD. Okay, excuse me. Okay, then this shows the details of the atom array that you can see after the rearrangement technique. So what you see here as a dot is actually the single atom image, and which is tightly focused with the optical tweezer. The rearrangement technique, as you see on the right-hand side, we impose, okay, this is done by spatial light modulator and high numerical aperture lens. But then we superimpose the light on each side and then make the tweezer depth and then move the atom. In that way, we can move the atom and then make an arbitrary array like in 2D. Okay, sorry. 2D and even 3D. Okay, so by using rearrangement technique, excuse me. So in terms of number of qubits, our headquarter R&D team already achieved 1,000 atom array, as you can see on the center, in a single shot. So it's not accumulated shot, it's a single shot. And then after rearrangement technique that I just talked about, it forms deterministic 228 atom array. And it's about a year ago, so now it's more advanced. Okay, so this is how we looked at atom as a qubit. So ground state is 0, and the excited state, which is Rydberg state, is 1 in this case. And then we drive, the external laser drive the transition between two, so that the amplitude and the frequency is the parameter to make the unitary transformation on this block sphere. So, for example, Rabi oscillation corresponding to the amplitude induce the X rotation, and then detuning, the frequency detuning from the resonance induce the G rotation. So, and that was about the single atom. And when you have a two neutral atom, it does not interact when it is in the ground state. To make them interact, you have to make those electronic energy level to the much higher excited state. We call it Rydberg state. So which Rydberg state is a metaspin stable state, which typically has principal quantum number more than 50. In that case, it forms a strong dipole moment so that it starts to interact when they are close together within a few micrometer. So that we define the range, so-called Rydberg blockade range. And if it comes close together within this range, the collective energy shift and then prevent them to be in the same Rydberg state. That's how we make partially entangled state between Rydberg atom, ground state atom, vice versa. So they cannot simultaneously excite together. So that's the very important property to make this quantum processor so that we can make control phase gate and consequently C0 gate as well. Although I don't show you in the detail. But one last thing I would like to highlight is the Hamiltonian govern this Rydberg atom system. So from this interaction, it forms Hamiltonian analogous to the Ising-Hamiltonian. So that this means this Rydberg atom array mimics the spin system. So that's why it's very natural to apply in quantum simulation to find a new material. Okay, I'll talk about this Hamiltonian in the later part to explain something else so that this is interaction term and then driving term as you see here in the first. And the second term is the detuning term. So in the measurement stage, we send the probe beam to read the 0 and 1. And after this push-out beam, or I call it probe beam, you will see the bright spot as 0, because if it's in the ground state, it excites and then emit. It excites and then emit the light. So that's how it's bright. But then if it was in the Rydberg state, it's not in the ground state, so that it already escaped, so you can see dark spot. So that's how we read the zeros and ones. Okay, so the processor starts by trapping a stochastic single atom, as I explained, that requires rearrangement, and then followed by quantum processing, either by entire system Hamiltonian evolution or individual qubit rotation or operation. So this shows the Pulsar Studio that you can use using our local emulator or emulator. So these dots indicates an atom. And then the lines shows the interaction between those among the atoms, and then the distance between two. At the bottom, you see the pulse sequence, simulation of the pulse sequence. So amplitude and the detuning. On the top right, you can see the quantum state in real time and the result at the end. So the pulsar that is used in the Pulsar Studio is a low-level software language, so that it designed the register array as a qubit and then pulse sequence as well. Based on this fine-tuned machine level language, we built cadence which is high-level software language that you can use like Qiskit. So neutral atom quantum processor is very powerful in a sense that it can be applied in many different computing paradigm. So you can use it for the analog quantum computing to by the evolution of the entire Hamiltonian on the total qubit system, or you can use it for the digital mode by gate-based quantum computing. Analog mode already shows demonstrate the result beyond the classical supercomputing capability, as you see on the right-hand side, which is a benchmark carried out in Paris several years ago for the quantum matters, which is the small spin array. So the interesting thing is, if we would like to replicate this result in the gate-based digital mode, we actually need large number of gates with excellent fidelity. Guess what? What do we need? So we actually need 10 to the 6 gates, number of gates with infidelity that is below 10 to the minus 6. So that's why now quantum simulation is leading the quantum advantage in quantum computing business or industry. So these are the algorithm that Pascal developed in mostly analog way. And those algorithms fall into 4 different categories. So quantum simulation, graph machine learning, and optimization, and even partial differential equations using differentiable quantum circuit. So let's look at some selected use case and algorithm if we have time. Okay. So for example, quantum evolution kernel that is already used in toxicity prediction. So in general, the graph can be mapped onto array of interacting neutral atom qubit. So if you remember what I just quickly described about the atom array and Rydberg blockade, so that nodes can be represented, atoms, it's encoded in the atoms, and the edges is expressed in terms of the interaction between 2 atoms. So that, let's say, neutral atom QPU is a powerful tool for studying graph data set. Do you agree? Okay, so let's look at the simple example for the binary classification. So in the case where the data points are graph object, the features are the numbers of nodes and edges. So let's look at this simple example. 2 sets of graph that looks similar, but then for any graph in the first set, there are a graph in the second set with the same number of atoms and nodes. But if you carefully look at it, the graph structure are slightly different in a way that the way of central nodes are connected, right? So you can tell between these, you can tell difference between these 2 very easily, but some classical classification can fails at this to solve this problem. So the question is, how do we distinguish in between top and bottom graphs? So we look at the second pair to illustrate it simply. So the first step is to map this graph structure onto the array of interacting neutral atom, Rydberg atom, located within the Rydberg blockade range using pulsar. Then we designed the resonant pulse sequence, Rydberg resonant pulse sequence with for the duration of 2.5 microsecond with the constant amplitude to excite all the register to the Rydberg state to recalculate the dipole-dipole interaction. And then this time scale is actually critical parameter in quantum evolution kernel, as I will talk about in the next slide. But then let's look at the final state and then sampling the final state to form this histogram, the probability distribution. So this normalized histogram indicates the number of atoms in the excited state. So as you can see, those two are distinct with each other. But then you can see the more number of atoms in the pentagon geometry. So this difference probability distribution can be, characterized, quantified by Jensen-Shannon divergence. Okay, I told you that this pulse duration is critical, and I skipped all the details about how to find the optimum pulse duration, but it should be trained to find the maximum distance between these two. So, similarly to what we've done in the previous slide, we arranged the graph on our interacting neutral atom like this, and then first define the graph Hamiltonian. This graph Hamiltonian corresponds to the interaction term in the Ising Hamiltonian. So to give a structure of the graph. And then we also define the mixing Hamiltonian in blue. This is transverse term of the Ising Hamiltonian. So if you can think about it, and then the next step is alternating the evolution of those two between those two Hamiltonian. And then you can change the time duration between these two. So theta is time duration for the mixing Hamiltonian, and then Ti is for the interaction or graph Hamiltonian Hg for every step. And then finally get the states, and then transfer to the probability distribution. Okay, what did I miss? Okay, so in that way, these parameters are optimized using classical optimization. You can do that. So then the important thing is we can train this, any graph type of data set using the alternating Hamiltonian. So, okay, so alternating these two Hamiltonian is simply, if you think about it as a mix, okay, let's put it this way. So mixing Hamiltonian proportional to the laser amplitude. So that this physically means we alternate turning on and off the laser. So in that way, we can train the entire system, and then maybe, okay. So in the final stage, again, the difference between two probability distribution can be quantified by Jensen-Shannon divergence, And then by exponentiating it with the free parameter mu, you can get new quantity, quantum evolution graph kernel here. Okay, so this is one of the examples to apply quantum evolution kernel on 8 random graph classification. And then also it was used in toxicity classification in a later research. But what I would like to highlight here is the fact that, you know, the atom-based graph encoding is much natural and geometrically uniform, as you see here, and it does not need index, so that it preserves permutation symmetry. Otherwise, if you look at the digital circuit, you have to give an index to express the graph, the same graph. And then that indexation might give you the impact on how you express the graph and additional extra information. So this graph, you know, using interacting neutral Rydberg atom to represent the graph type of data set is much natural and very practical. So that QEK can be applied in, you know, industry sectors, including energy, finance, manufacturing, drug discovery, and transport and logistics. And it also increased the accuracy and speed depending on the data type you are considering. So, okay. So I can quickly move on to the next one. So other, you know, mission planning for satellite using solving MIS problem. This is, okay, so we have a constraint and then consisting of 400 nodes MIS problem. And then telecommunication network, planning by graph coloring, and chemistry, toxicity, drug discovery and toxicity screening by using other algorithm that PASQAL developed. So to find the location of water molecule inside the folded protein, and toxicity prediction that I just explained using QEK. And also, yeah, the amorphous solid is also strongest point that we can, you know, strongest candidate that we can explore using quantum simulation. And we also provide some risk management solution quantum algorithm. Also process optimization. So I would like to summarize my talk by telling you that you can explore more natural way of using quantum computing as Richard Feynman described in the 90s. Okay, thank you very much for your attention. Any question? Time's up. Okay, you can you know, come to me anytime later if you have question, and thank you very much again.